Those who just came in, this is a general gallery that you can find online in Herwig Hauser's homepage. It's a gallery of singular surfaces. So these are, it's a selection of plots of different surfaces in 3D space. So generally just one equation, an irreducible equation. And you'll find this kind of gives you a picture of the variety of the objects we're getting. So the problem is that these things are in the real space. So if you actually would like to have an algebraic picture, you need to have complex numbers here. And the problem is that you can't really visualize them very nicely. So this is why we have some very weird things happening. For instance, this is called the Whitney umbrella. So as you can see, it's you have this surface part here, but you also have this stick coming out of it. So you expect something a little bit more, but this is the problem with plotting only real points. Okay, so this is just to introduce in a very leisurely way the objects we're going to study today. This is another surface that I mentioned a couple of months ago. So this is a surface where if you take a vertical section, you'll obtain the node, just like this one here. And if you approach this particular difficult point to understand, you'll obtain a cusp. So this is a very interesting example, and so on. So, okay, I'll let you browse these things on your own, but okay. So, but today this was just to introduce a little bit what we're going to talk about today. Today we're going to finally go into the study of singularities proper. So. So the chapter of today, which is this isn't neat anymore. So today we're going to finally start 5 on smoothness and singularities. Okay. So as we already mentioned, we already talked a little bit about the dimension, right? So so my starting point will be trying to come back to this idea of dimension. So remember that we had a topological definition that basically just gave us cool dimension. Right? So this was a very interesting achievement. So the idea was to say that if we had two irreducible varieties, and one is strictly including the other, then the dimension there should be a strict inequality between dimensions. So this is the basic idea, the cool dimension. But we want to go back to a more geometric intuition, and we want the dimension to be something like the number of local parameters around the point.
Excuse me, I don't remember if you comment. Is there any relation with the so-called transcendental degree?
Oh yeah. Yes, I commented that already. Okay, so let's recall the thing about transcendental, the link with the transcendence degree. So if you have a affine domain, that is the coordinate ring of an affine irreducible variety, so let's say irreducible, well, it's in the definition, but it's worthwhile coloring it, find variety, then the dimension of x will only be the transcendence degree of the fraction field of the coordinate ring over the base field k. Okay. Now we also know that this is also equal to k of x, the function field of x. Now this is actually a bit difficult thing to state because if we go outside of the types of rings we obtain, like A of x, then this doesn't really apply. Especially if you take, for instance, let's say, rings coming from number theory. So, for instance, how do you call these number fields? Then this doesn't really apply. Okay. Let's see. So my idea was to go back to the geometric intuition. So especially coming from differential geometry. In differential geometry, this has a very specific meaning, right? Well, this at least gives us the idea of a tangent space. So if we have local parameters, then we can approximate locally the neighborhood with a linear subspace called the tangent space. Right? Approximate locally by linear subspace. This gives us tangent space. Now this is kind of the starting point for today, is that we try to find out what is the relevant notion of a tangent, at least a tangent line, in algebraic geometry. What is for these algebraic varieties? And this is what we're going to start. This will be the first point. So tangents to an algebraic geometry. So for this, we use the following intuition. So a tangent should be the limit secant of tangent at a point, let's see, zero limit of seconds as they get closer to zero. So if we have a variety, let's say something like this, we have a point 0, so this is the variety x. We want, let's see, we don't really have a color. We have a second going through this point 0, right, that we are interested in. So this is a second. And this will cross the variety at another point, and we want to bring this point as close as we can to the 0, and that will make us a tangent. But there's some ambiguity because we can approach it through here or through here, and that gives us several possibilities. So I'm going to give you a construction that will give you the whole set of tangents in one simple manipulation. So for that, we need to, I will give you a construction and then I'll explain why it is relevant. So bear with me. So, okay. So let's just say, let's just assume that up to a linear change of variables, we are interested in a point 0 of x. So just like an integration, right? Okay, and we construct the following thing. So, we'll consider points, let's see, x, t, okay? So, the points x will be in A and of k, right? So, x will be embedded in A and of k. And t will be just one linear parameter, and they follow the following properties. So t will be different from 0. That's just, sorry, you'll see why this is important. And xt is in x, like this. Now the problem with this is that it won't be necessarily a closed subvariety of an plus 1. So what I do is take the Zariski closure, right? So this is Zariski closure in n plus 1, okay? And so, and I define the tangent cone. This is what's called the tangent cone. As the AN projection of x tilde with v of t. So you take this closure, and this would add points in the t equals 0 section, right? So these are the extra points that are interested that I am interested in, and this will define the tangent cone. So this will the written c of 0 of x. So now that I gave you this construction, I'll try to explain to you why this will give you the tangents at 0. So for that, I'll draw you a picture of what this actually means. Okay. So imagine that we have here, let's see, how do I, okay. Let's say that I have the point 0 here, and then I have a simple cusp, right? So this is x. It is embedded in A of 2. Simple as. Now, inside this AN plus 1, so A3, so I have a space here. Imagine I have a space here. I will take, I just want to look at one horizontal section of this x tilde space. So what happens for t equals 1? Well, for t equals 1, I just need that to have points x that are in x. So this is just a cusp again, the exact same cusp. So let's see. I have the same exact cusp here. And what's interesting is to see what is going to happen between this section here and the section t equals 0. So I'll draw a couple of intermediate points. So what happens when t is getting smaller? When t is getting smaller, the point, so in order for this to remain in x, we need the points x, so the x coordinate here, to get bigger. Right? So you need to make them a little bit more distant from the original point 0. So these two, so imagine that we have this cusp. So we have these two pieces, let's say. Well, they'll get farther and farther away from 0. So maybe it will look a little bit like this. If I go even lower, then they will get even farther away from each other. And as you can see, they kind of, as these as these things get farther and farther away, they get elongated. So imagine like a elastic piece of elastic that gets stretched out more and more, and as it gets more and more stretched out towards infinity, they become more and more linear. So this is why, when you stretch them out to infinity, they become only two lines. So this is what it will look like. Of course, there's an extra added piece here because well, we're considering, again, this is a real picture, and in complex numbers there should be something here on this other side as well. Okay, so this is why the tangent cone is defined kind of like this. It's basically this picture, and this is the final image will be this part here. So this whole thing in green, I suppose, is x tilde. Now this construction is actually a very common construction that I haven't talked about. It's called a blow-up, but we didn't really talk about it because I don't really have too much time. And this part here is an exception, is a strict transform. Okay, but how about equations? How can I compute these things in actuality? Well, we just need to take account of this thing, right? So let's see. I take a point xt and I try to see what are the equations that this point will have to satisfy in n plus 1. Well, I have the ideal of x, and I need to verify every equation inside this ideal. So f will be equal to fx. Yes. So, and t needs to be different from 0. That's just an extra condition. Okay. Now I need to use a tool that we already mentioned a little bit, especially talking about the projective space. We need the homogeneous decomposition, right? So let's see, what are my notations? So this will be inside of x. This is the homogeneous decomposition. So that means that every fk here is a homogeneous polynomial. This is degree k, this is degree k plus 1, degree l, and so on. So why did I change this like this? It's because now I can write fxt, this, I can factor out the factor t outside of each of these homogeneous parts. So I will have tk f of k x, and you can see this just concern, this is just x here, plus tk plus 1 f of k plus 1 x, plus so on till t to the power l fl x is to be equal to 0. Okay, and t is different from 0. But wait a second, if t is different from 0, then I can factor it out. Because all of these are divisible by t to the power k, so I can just get it out, right? So this is equivalent to for all f k plus I of x, then I have f of k of x plus t to the power 1, right? F of k plus 1 x plus like this. So this is actually, so these equations are going to be our equations for x tilde, right? So what about Okay, sorry. Well, this is now x tilde thus is the annulation of f of k plus t of f of k plus 1 plus for f in I of x. Okay, so we now have the equations of x tilde. So we just needed to cross it out with the simple equation t equals 0 to obtain the cone. Simple as that. So C of 0 is just going to have as equations all of these equations here. Sorry. And t. There's an extra equation here. So, but what happens if I have t equals 0? All of these terms disappear. If t is equal to 0, then all these terms are just out. So what is this? This is f of k with f and x. Now, the f of k has actually a particular name. It's called the initial term or the leading term of a polynomial. Okay? So let's give the name for a decomposition, homogeneous decomposition, sorry. F of k is non-zero, is called the leading term. Well, let's say it's it depends because sometimes so this is something that is used, the leading form of f or its initial term. And I prefer this one because this is it's closer to the actual notation that we use for this homogeneous component, written like this. So, in summary, if we want to have the equations of our tangent cone, what do you do? Well, if okay, so if x it comes from these equations from an ideal I, so let's assume it's reduced. Okay, remember the Newton's Zatz, we need reduced ideals. Then the tangent cone at 0 will only be the v of the initial part of an ideal. And what is this? This will be the ideal generated by the initial terms, yeah, of the members of I. And this is where I need to make you aware of some pathologies that come up in this situation. So if I have generators like this, and I want to take the initial form or the initial terms of the ideal, this will usually not be the ideal generated by the initial terms of the generators. And for that, I'm going to give you the simplest example we have. And this again has a lot of there's a lot of discussion to be had about this, especially concerning Grosbe basis. The fact is that this is not true unless we have a special generating family here. So counterexample. So C counterexample. Consider two generators. So let's see which one I chose. So there's x squared and xy plus y cubed. Okay. Very simple stuff, right? So the initial terms here is x squared and xy. Okay, very simple. But you also have other types of monomials inside the ideal generated by these. So I can actually eliminate these two and obtain a high monomial which is purely made of y. So let's see. Which one did I choose? Let's see. Did I mess this up? Probably. Let's see. Oh, okay. Maybe just like this. Yeah. Well, if I have f2 minus, let's see, y of f1, well, I just eliminate one term and I obtain y3. Right? So this is a monomial, so it is the initial idea of f1 and f2. But y3 is not in the ideal generated by the initial forms. Why is that? Well, this is generated by x and xy. So this is actually just the ideal generated by x, and y cubed is not multiple of x. So this does not make sense. So one should be careful about these things. And again, if you are interested in more computational stuff like this, check out Grobner basis.
Are there always suitable bases for which we have equal?
For which we have this suitable, well, let's see. Yes, you need to have Grobner basis, but for a specific monomial order. Grobner basis depend on the monomial order you choose, so you need to choose a specific monomial order for this to work. But yes, you can have. Now, okay, the only problem is that usually to implementing, if you study the algorithms that are beneath this thing, it's kind of complicated stuff, complexity-wise, but it's usually in experience, they work relatively fast. Okay. So let's give some examples. So instead of giving you the classic example of, well, okay, we already had a kind of idea of what the tangent cone looks like for the cusp, but this is actually pretty easy. So let's try to give some. So let's give this thing very quickly. So the cusp is this, usual cusp. So we'll always study the at 0. Sorry. So this will be, the initial term is y naught, like this. So as you can imagine, we only obtain this horizontal line. Now the problem is that we have a y squared here. So in actuality, you really need to have double line here. So this is one of the problems we face, is that we obtain multiplicities. Okay, so let's see a node. So a node, this is even more classical, equals x. So let's see, the curve is classical stuff, this. Now the cone here is supposed to be, let's see, we only have one equation, so the degree here is 2. Right? So this is y squared minus x. And it's actually the union of two lines. We just factorize this. Okay, so the two lines are here. So maybe another example just to show that, okay, maybe this cone actually gives us valuable information about how to plot curves. Let's say I give you the following equation. So x squared y minus y cubed plus y. So this is a little bit more difficult. We don't really know what this looks like, but I can just be interested in the tangent cone, and maybe that will help me to see a little bit what this looks like. Okay. So this is degree 3, right? Degree 3, 4. So, but I can factorize this. So this is, I can factorize y, and then inside I'll have the difference of two squares, x minus y and x plus y. So I have 3 lines. Okay. So I have 3 lines, the 2 bisectors. And the horizontal line. And in fact, if you look a little bit closer to what this looks like, you will obtain a sort of butterfly curve. Like this. So, can you have a look at the next picture? Okay. So this gives you the so the tangent cone. What you need to remember is that it gives you the different tangent directions to your variety at a specific point. But wait a minute. The thing we said here is the following. The tangent cone here can be a nonlinear space. So what is this all about? So remember that our goal was to obtain a linear space, so that vector space, right? In order to define the local dimension. So this has given us an object that is interesting, but not what we're looking for at the beginning. And in order to find this thing, we need to look at what's called the tangent space. So, okay. So let's get back to our setting, right? We have, let's see, okay. We have a variety, an affine variety inside of A and of K. We always more or less reduce to this case when we try to define stuff, for the simple reason that singularity is a local notion, and we know that up to taking a neighborhood around the point, we can always reduce to this. Okay, remember, this is just to remember about how we constructed the projective plane and how we discovered affine charts. This is what I was referring to. Okay. So, as we already did, we can assume that A is equal to 0 without loss of generality. This is what W of means. And we define the tangent space as follows. As t of 0 of x. So I'll have a set of equations. So you need this to be a linear space. So what do you use? Well, you simply use the linear part of your equations. Right? So this is linear part of f. Now remark that f, since they go through 0, so if they vanish at 0, that means that they don't have any 0 component. They don't have a constant component. So they have linear, quadratic, cubic, and so on components, and I only am interested in the linear parts. So this is actually going to be a tangent space, a vector space inside of A n of k. You can assume this is a linear space inside of A n of k. And here, let's make and in some way you can imagine that it is the smallest linear vector space that contains the tangent component. This is more or less the intuition behind the tangent space, right? So just to compare it a little bit with that. So the thing I just said here is that, okay, the tangent cone is always included inside of T0 of x. Why is that? Well, if I consider the initial forms of a polynomial, usually it will be bigger than 1. So if f1 is 0, then there's nothing to check. If it is f1, then it is an initial form, then it is in the equations of the cone. Of the tangent space. So this is a very easy verification to do. Okay, and here a nicer thing to see is that if the ideal of x is generated by polynomials f1 to fn, then T0 of x is, well, the notation is a bit wonky, but you just need to take the linear parts of the generators here. This is a lot nicer than the equations of the tangent cone. Like that. Okay. So, well, maybe let's see. Okay. And actually, this gives us the very first definition of what a smooth point is. Right? The discrepancy that comes from singularities is encoded in this inclusion here. Right? If this inclusion is strict, then the point is singular. If it is not, then the point will be smooth. Okay. So where is the definition? Here. Okay. So the point A in X is, so there are several terminologies for these points: smooth, regular, or even non-singular. If the cone and the tangent space line. And otherwise it will be called a singular point. So for when this condition fails, there's generally only one term. There's also a known terminology for these points. We also call them simple points. This is the literal translation from Russian, and this was particularly used by Zariski. He was doing his work on singularities, but this word fell out of use. So I won't be really using this one. And is singular reference. So take like this. And I also explained why we use this word regular, because the smooth and non-singular we can kind of see why it is. But there's a particular interest for why you use the term regular. And that's linked to commutative algebra, and yeah, I think I'll have the time to get to that. Okay, so so in fact, one of the there's actually we are more or less, let's say, obligated to go into trying to understand a little bit closer these objects for the simple reason that we want to obtain a simple computational criteria. For now, we don't really have we have a vague idea of how to get the equations of both of these spaces, but we don't really have a concrete computational idea. The goal I have in mind will be the Jacobi criterion that will give us equations for the smooth smooth locus of a algebraic product. But for that, we need a couple of algebraic tools for that. Okay. Unfortunately for that, I'll have to use some black boxes coming from dimension theory. Okay. So one of the first things you can see is that there is an isomorphism between the tangent space X and the dual of a particularly quotient. So this is the k-linear dual where Mx of A is the maximal ideal of the local ring of our point. Okay? So this is a finitely generated ideal, and when we quotient it by the square power of this same maximal ideal, you obtain a finite K vector space. This is mostly just Nakayama's lemma. So let's see. Maybe I can accelerate, but the basic idea is to first. I don't really have enough space here. Okay. Okay, so well, this is the first statement. So I'll just try to give you a sketch proofs for the basic ideas how the proofs work. But the second statement is that the coordinate ring, if I want to compute the coordinate ring of the tangent cone, I actually obtain a very specific type of algebra here that is also linked to this maximal ideal. And here I need to make careful use of the natural numbers. For me, the natural numbers will always have 0 in them. Okay, so this, okay, maybe I can give a sketch. So step 1, you can replace in 1 and 2 MXA by MA, which is just x1 minus a1, xn minus an, which is the maximum area in the coordinate ring and not just the local. So going from one to the other, it just amounts to localizing, and localizing doesn't change any of these expressions. So that's step 1. Then step 2 amounts to finding specific isomorphisms between these things. So finding isomorphisms, so I'll just give the basic one-dimensional 2. Let's see, can I? Yeah. So, let's see. Yeah. So, for instance, so the first one is going to take MA over MA squared. So this will be the dual of x, right? And how does this work? Well, I take a regular function, function in the a of x, modulo m squared. I take its initial form that I reduce to the tangent space x, like this. Right? Remember that both x and the tangent space are embedded in a copy of an, right? In the an space. Okay. And this is actually an isomorphism. Right? So I won't prove it, but I'll just show it how this works. And for the second one, so for the tangent one, the idea, well, let's see, how can I show this? More or less. Oh, okay, yeah. So, for all k in the natural numbers, I'll have the following thing. So, I can consider well, what these things look like at 0, let's say, and let's just assume that a is equal to 0. This simplifies a lot of stuff. I don't have to carry out all these AIs. So, what do these things look like? So the xi's are the images inside of, maybe I can show this, are the images of the coordinate functions inside of AX. Right, so what does this look like? Well, this will actually be isomorphic to the ideal inside of the polynomials, so not the coordinate ring anymore. But I'll have to quotient out a bit more of the equations. Okay, I don't have enough space here. Let's see, so, and the extra equations are going to come from I of x crossed with this component here. But the interesting part is that in this ideal here, I can consider all the equations inside of I of x of multiplicity of order at least k, and mod out all the higher parts, or the higher homogeneous components. So actually, inside of this part here, I can just focus on the initial terms of the elements of X. So this is the very interesting idea. So this is the degree k monomials in the initial idea of, well, not monomials, but components. Sorry. Like that. And this is actually the thing that allows you to go back, to link it back to the equations of the tangent cone. So this is the actual really difficult ingredient in showing that there's an isomorphism. Okay, so this is just to give you the idea here. Now, the other thing, well, once we have these let's say components, I can use dimension theory to establish what are the dimensions of all of these two objects. Right? So unfortunately, I have to use some stuff around some others that I can't really introduce. So for that, I'll just send you to Atia McDonald's book, and basically I'm going to use theorem 1114 that introduces, among other things, the Hilbert-Sumner function and the characteristic polynomial of a local ring. Unfortunately, this is how we are going to use the to find out what the dimensions of these things are. So, well, the first thing we can stipulate is that the dimension of the linear space is simply put the dimension of this quotient, right? And here, there's an ambiguity because the linear space, its dimension is also equal to the crude dimension. Okay, that's basically easy. But unfortunately, the really interesting part is about the dimension of the tangent cone. So the dimension of the tangent cone, if you remember what we said about the dimension, the cool dimension, it is equal to the dimension of its coordinate ring, right?
Andrea, what do you mean by cool dimension? For the
Here?
Yeah.
Yeah, this dimension, the dimension of a linear space is also equal to the cool dimension of this linear space. Now this is because the dimension of A of n is n.
I mean, in terms of the reducible nested sequences of linear subspace.
Yeah.
Of course.
Chains of closed subsets. Of course. So, but we saw that this dimension, this coordinate ring, is isomorphic. We can still have it right there. It's isomorphic to this direct sum, which is actually a graded ring. This is called a graded ring. So, like this. And the dimension of graded rings that come from a local ring is also equal to the dimension of the local ring itself. alpha that comes from this theorem here. Right? So, and we can also go a little bit further around, and this is also defined as the, it's a small bit, but the codimension in X of the singleton A. So you single out the point A and you look at the codimension.
We're good.
Okay. Could we see this a little bit simpler? I didn't find out because I did try to look around to see how could you arrive at this in a more simple way, but I didn't find some satisfactory idea. Generally, if I wanted to stray around from this, I would have tried to complicate things a little bit more. For instance, I would have come closer to the cone construction.
You know, there is a problem with this equality because if you think of in terms of affine spectra,
yeah,
it has dimension one more than the dimension of OX.
Yeah, because you take the projectives.
Yeah, so this is really the dimension of the approach of that thing. As it's written, it's not correct. That's
well, actually, yeah, because let's see. Well, the fraction field, you know that the fraction field you need to take the zero components when you take the projective space. So that actually takes the dimension one less. So somewhere this is true. Somewhere. There's an error, but it's compensated by a second error.
Two errors cancel out.
I think something like that.
That's strategically placed.
Okay, so what I wanted to say, let's not. I don't want to derail your talk, but so this thing usually this is expressed as a a Risch algebra of an ideal.
Yeah.
In this case, it will be associative gradient.
Yeah.
So I think it's not that hard to see that the fraction fields are the same. Well, there will be an extra variable, so you have to take the approach construction and all that. Because proving that they're birational or whatever makes
if they are birational, then
yeah, but it's not the case exactly because this corresponds to the exceptional divisor of the
yeah.
Okay, anyway,
just
forget about it. Let's move on.
No, but it's because there's the cone is defined like a blow up, which is a birational morphism. That's kind of how that all goes together. So what was I trying to? Oh, okay, yeah. So I wanted to go back to the thing. So we'll have that a point AX in a variety is smooth if and only if. Well, now we have a very concrete idea. If and only if we have equality between these two quantities. So. And why is well, of course, if the cone and the tangent space are equal, then the dimension will be the same. But even more than that, since the tangent space is irreducible, any algebraic subset which has the full dimension of this tangent space will be equal to the whole space. So the last ingredient about this is that if, let's say, has full dimension, full cool dimension, a numerical criterion to establish if a point is smooth or not. And in fact, we can even push this a lot more and obtain what is called the Jacobi criterion. Well, this will actually give us equations of what we need here. Okay. So we take a point inside a fine variety. So this is a fine variety. Sorry. And I take generators of the ideal lengths. Right? So let's see what are my notations. And I take generators there. Okay, so these are equations that cut out through a point A, and we can have the following criterion. So A is smooth if and only if the rank of a particular matrix, and this will be called the Jacobian matrix. So I take the partial derivatives of these fi's, right, in f variables, and evaluate them at A. So this will give me an actual matrix with entries inside of in K, the base field. Right? The size of this thing is, well, it's plain obvious. It is called the Jacobian matrix. Yes? And we want this point to be smooth if and only if, let's see, is it the smooth one? Yeah. If and only if n is, this rank is larger than n minus the codimension at A. Like this. And, okay, so this is, well, this is the affine version. There's also a projected version, but let's see here. Okay, so let's see, where could I put the affine version? So the projected version starts off the same way, but we want these to be homogeneous polynomials. And the conclusion is mostly the same. Well, the formulation is mostly the same. So we have m components, but here the problem is that, well, the difference is that we will have an extra variable that we need to take into account, like that. But it also needs to be bigger than the same quantity in the affine case. And the reason is there's an extra relation coming from the either homogeneous identity. Okay, so this is something, well, it's smaller.
Can't you just, because, I mean, you look at the definition of a smooth point, right?
Yeah.
So can you just say that a point of projective variety is smooth if you look at the affine open at that point?
Yeah,
When they used to.
Yeah, but the problem is, well, the problem is that you need to dehomogenize these equations,
Yeah.
basically. But then, if you consider the partial derivatives, there's kind of a mix-up. This is just to go a little bit faster. You have the homogeneous equations, and instead of going to the affine open, you can go directly to the homogeneous equations.
Yeah, because usually the affine open is you invert one coordinate.
Yeah.
I mean, what I wanted to say is that the property of being smooth is really a local property.
Yeah.
A point here.
Yeah.
So it's an affine thing.
Yeah, it's a local property, so it should just be this. Yeah. So, what else do I want to do? So, okay. So maybe if okay. So maybe one of the things I wanted to point out about this before I go a little bit further is that why did I also use the word regular? I wanted to justify why did I use the word regular until now. So one of the first remarks I wanted to make is that a local ring, or usually we write it like this. A is the ring, M is the maximal ideal, and K is the residual field. Is regular. Okay, well, utility. Sorry. Local ring is regular if and only if the dimension of A is bigger or equal to the dimension of M over M squared, and in all generality we have the inverse inequality. So this is the vector space here, and this is by Nakayama's lemma. This is just to mention the commutative algebraic reason that works here. So by the corollary that is on the left-hand side, a point A is smooth if and only if the local ring is regular. Like this. So this is why we also use the terminology of a regular point. Yeah, like that. Okay. And okay, let's.
Andrea, I'm a bit confused with this. What do you mean by all generality we have the reverse, but if it's regular, so then it must be equal?
Well, yeah, but that's, well, it's a direct application, but. Yeah, I know, it's that very generally proves, we try to prove the inverse inequality in order to show that.
Yeah, but it's never strictly bigger.
Yeah, no.
Yeah, so.
Let's see. Oh, yeah. This is also equivalent to saying that M is generated by D equal dimension A elements. Yeah. Well, the idea is to take the elements that generate the ideal M, and that would be equivalent to saying that they generate a basis of this vector space on the other side. So, like that, and we say that any D, if I now take the geometric equivalent of this, if I take any D generators inside the local ring of a point, any D generators of maximum ideal are called, so what was my terminology? Local parameters. at A. Like this. And one of the, let's see, where is it? Okay. One of the interesting things is that if you come back to this affine case, so this are generally just take elements in M that form a K basis in M over M2, right? So we know that. So if A is equal to A1 to M, we can take local parameters among x1 we can take local parameters to be linear factors actually. So this is very close to what happens in differential geometry. So the local parameters will already be the coordinates, the local coordinates around the point. Okay. So this most definitely brings us back to the original intuition of what the dimension was. So, okay. Now, let's see. Oh yeah, sorry, I need to. Okay. So, okay, let's take a small break before we conclude this whole discussion with a couple of these results. Let's draw some pictures. A couple of pictures just to see how these things work. Right? So let's consider a cone. Not the projected cone or the affine cone, a real actual cone. Let's consider, right? A cone, right? That goes through the origin, x, y, wait, no, sorry. Z here, y, yeah, I don't know why. Like this. So how do we look for the singular points for a variety? This is a real, because we talked about with all these nice pictures, we often have the real plot of the surface may be misleading. So how do we do it? Well, now we only have one equation, so you just need to take the Jacobian matrix, which is only the gradient of this equation, right? So let's call this f. The gradient of f will only be, well, x to y negative to z. So if characteristic of k is different from 2, of course there's a problem if the characteristic is equal to 2, because this will actually factor. If the characteristic is, because of the Frobenius, this will be actually the square of a linear factor, which is not really. So the characteristic is different from 2. So, okay, maybe one of the problems is that I didn't give it a name, but the singular locus is just reduced to the origin. Okay, very easy, right? What about the interesting equation I gave you? I talked about the Whitney umbrella. So the equation for this beast is x way we draw this thing is by first drawing a nice line like this, and then we chose a point here, close to the top. You draw a big line, you draw a small line, you draw another line here. Okay, so it's a drawing cross. So, and then you draw a nice line like this, and you draw the same one here, but be careful because here it's behind and it comes back here.
In fact, this really was an umbrella.
Yeah.
Like a Victorian era, like 19th century, whatever.
Yeah,
because it doesn't look like a modern umbrella.
No, it doesn't look like a modern umbrella. Like the whole thing about this is like you take a surface like this, and then you pinch it. So this is why Hatching calls it the pinched surface. You pinch it along this vertical axis, and you can imagine that if it's large enough, it will be something like that. And this is kind of the funny thing, is that we don't really see it, but it has also this kind of tail, or like handle of the umbrella, right? That goes infinitely like that. And the singular locus is actually this whole vertical line. I haven't decided that this is the origin. The problem is that the axes are not classical, right? This is x, this is y. So the singular locus is the y-axis. Well, the reason is fairly simple. It's because let's call this equation g, and I'll write it here. So the gradient of this is z. This is 2xy and x squared. So in order for this to be 0, you need z to be 0 and x to be 0. So this defines this equation. Okay. So this is kind of a nice picture to have in mind to see that these things are a little bit complicated. Okay. Of course, if the picture would happen in a complex plane, it would be much more complicated. Okay, so the last two things I wanted to talk about, and that will actually more or less close the general knowledge we need about singular points, is genetic smoothness. So another corollary of the Jacobian criterion, the Jacobi criterion, is the following thing. So it means that the set of smooth points is open. So the idea is to take the Jacobi criterion and actually reformulate it in terms of algebraic equations. But the fact that you have the rank of something being bigger than a fixed bound, that is an algebraic equation, because it amounts to saying that some minors of the matrix are non-zero. So that defines an open space. Okay. So that's more or less the idea of how we prove this. The second statement is a little bit more difficult. It's called the genetic smoothness. It says the following thing. It says that the smooth locus is a dense open subset of our irreducible variety. Now this is a little bit more difficult because to prove, but you can see it in all the pictures we did. Here we have a line and the surface is two-dimensional, and if we take out the line, we still have something which is dense, right? So this amounts to saying that the smooth locus is not empty, whatever count is set there. 2 minutes and wait. I still have 5 minutes, right?
Yeah.
Okay. And in order to simplify this, we need first to reduce to a hypersurface. And in fact, any algebraic variety is birational to an hypersurface. But that's kind of complicates most of our discussion. Let me see if I can. Well. Okay, so idea of the proof. So reduce to a hypersurface. So any variety is birational to a hypersurface. And you remember that birational morphisms give you an isomorphism between open dense subsets between two varieties. So this is actually a reflection. So let's suppose that we have a hypersurface like this, and we can also suppose that it is irreducible. So this means that F is irreducible. And let's suppose that it is wholly single. That means that we know that it is an open subset, that the smooth locus is open on the first point. So in order to show that it is open dense, we just need to show that it is non-empty, because open subsets of irreducible topological spaces are dense, right? We just need to show that there are smooth points. Suppose otherwise. So that means that for all of the variables, df of dxi is limited to x is 0. So what does that mean? That means that df of dxi belongs to I of x, and this by the Nordstrom Satz, this is equal to f, right? But wait a minute. The partial derivative of f and the polynomial f have different degrees, right? This is degree, let's say, k, and this is degree k minus 1. So what does that mean? That means that the partial derivative is 0, because this is irreducible. Okay, so that means that. So this is mostly a basic idea in field theory. If all the partial derivatives of a non-zero polynomial are 0, that means that either f is constant or f can be written as a polynomial in powers of p. And the characteristic of k is positive. Right? But remember that our field is algebraically closed. So we can find f tilde such that f is actually f of x1 xn to the power p. And this contradicts the irreducibility of f. And in fact, the requirements photogenic smoothness is not so much that the field is algebraically closed, but it is that it is perfect, in fact. And just as a reminder, a field is perfect if and only if the Frobenius, so elevating to the p-th power, is subjective. So everything is a p power. Okay, so I think I'll stop here. Next week, we'll talk about completion, the coin structure theorem, and hopefully we'll start talking about curves and a very more specific example of how these work in that specific case. Okay, perfect. Thank you.